Yes, I want to know, is that really more efficient?
Unless you're using
I that doesn't sound like a good solution.
I'm seeing you much less than these artists.
Yep.
This one might lose it. I love it.
Again, the test number one is coming from next Monday, and then the scope of the test is going to start from the chapter 1 to 3, up to the point that we finish right here. So this is the last scope, last part of the test number one. Okay? So again, this one here actually is say this is a 3D shape. This is actually a 3D shape that you draw in space. And then because it's a 3D shape, it will have a coordinate system for each individual point. Okay? It will constitute this shape right here in space. So we got all the coordinate system, the big coordinate system to make this shape in space. And then what I'm going to do is to show you how do we rotate this. What if the question is what if we rotate around around z-axis by 45. So someone wants to rotate this shape in space around z-axis by 45 degrees, and then we'll see how this will look like, okay, on this y-z plane. That's the question. Okay? So we'll try to find out all these data points, 3 data points after rotation, and then plot them on the same plane, y-z plane, to see how it looks like after rotation. Okay? So in order to do so, we'll define the P, which is the transformation matrix that we discussed last time. Transformation matrix that in this case I'm going to call this the R. R. Basically, we are asking for a rotation around Z. So I'm going to say RZ 45, and then put prime, just to mention that this is the moving coordinate system. Okay? Moving. So moving means that if you have multiple operations, it has to go this way, from left to right. If it's fixed, you take this prime out, and then it goes backward. Okay. But if it is moving coordinate system, you just stay with it, multiply whatever it comes after. Okay. But this one here only just requires the rotation around Z. Okay. So that I have only one of them, RZ. So what you have to do is to have the matrix all formed, 4x4 matrix. And then if you work on this RZ, RZ around Z by 45, then you will find that the matrix in your textbook, we discussed those several times. So this one's the C45 for sine 45, negative sine 45, and then a 0, sine 45, and sine 45, 0, 0, 0, 1. That's the rotational matrix. Okay. For the case of the rotating around z-axis by 45 degrees. Again, you just if you can't find this, just go back to the original definition of the rotational matrix, okay, and then just to figure out the all components. Okay? And then because there's no translation, it has to be 0, 0, 0. And you fill the last row with the only 0, 0, 0, 1. Okay, that's your transformation of 16. Now, if I have this matrix set up, then all you have to do is multiply these coordinates to the, just like the P. If you remember, PA is what? What was PA? If I know T. TAB, right? AB times PB. So what I'm trying to find out this guy for a given P. PV by multiplying this into the transformation matrix T. That's all I want to do. That's all I need to do. So the new coordinate system, new coordinates for 0, 0, 0, for example, first of all, 0, 0, 0. If I multiply 0, 0, 0, right here, 0, 0, 0, and then at the end, you need to add 1 there, because to make these compatible with the four-line matrix, just add 1 dummy. So what if I multiply 0, 0, 0 to this? What do you think is going to happen?
0, 0, 0.
Just 0, 0, 0. So 0, 0, 0 will map to 0, 0, 0 as a result of multiplication with the transformation matrix. Now the second is, let's say this is my P1, first point, second point, third point. So let's just move on to the second point, which is 0, 10, 0, 0, 10, 0. So what I like to do is just multiply 0, 10, 0 to this transformation matrix T. Okay, and then we get the result out of it. And that gives us, let us add this in here. Just make sure that make it compatible with the multiplication by 4 by 4. So 0, 10, 0, if you multiply that to the T matrix, that's going to be negative 7.071 and positive 7.071. Okay. This is the result of the multiplication of your previous matrix to the transformation matrix to get your new coordinate system. Okay? And then the third one is what? P 058. So I just have to plug in 058 right here, multiply to the transformation matrix. And that'll give us negative 3.535 and then 3.535 positive 0, no, 8 and 1. 8 and 1. That's the result. So with those results of this multiplication, what I'm going to do is I'm going to plot these resulting vector points onto the y, z plane to see how it looks like after rotation of 45 degrees. So in order to do so, I'll just plot these points, on this space of the y, z plane. So 0, 0, 0 is the same right there. It stay right there, same place. Second one is what? X, Y, Z. So I need to have these two data points. Y along Y 7.071, somewhere around here. And then what? And then Z is 0, so it has to be right here. That's your P. I'm going to say P2 prime. This is P1 prime. Okay. Viewpoints. And then if you move on to the third one, now you have to collect the Y, Z data points to plot on this space right here. Y, Z is what? 3.535, 3.5 somewhere around here. And then Z is 8. It goes all up to 8 right here. So here's P3. Okay, P3. So if you connect these three dots, it's going to be something like this. So this is a result of rotating 45 degrees around Z. After you rotate, if you see on the plane of Y and Z, it's going to be a little bit skewed, right? Skewed. So that's how you actually accomplish the transformation of any 3D shape in your space. This is a simple example. I mean, the same thing will happen, applicable for any 3D models that you have. As long as you know those vertices, okay? Vertices of the data points, then you just multiply. So this is a kind of a use of the transformation matrix to operate the 3D models in your design space. Okay, design space. Any questions for this? Again, this is the last part that will be part of the test number 1. Okay, so you may expect to see some problem like this maybe in test number 1. And then I'm gonna also thinking about having the coordinate system, the one that we just discussed. Remember the coordinate system in space? Okay, changing one coordinate system from here to somewhere around here. Okay, so you have to know how to transform what it takes to actually move from here to there. Okay, and you can it is your choice to go either fixed angle or moving angle. Okay, but from my understanding, moving angle is much easier because you don't really have to go back to original for sequential sequential operations. You just have to refer to the just previous one, okay, to apply the moving angle. So go from there to finish the entire sequence of the moving coordinate system. So this is possible questions. This is another possible questions. And then what else we have? So there are some homework that we discussed last time. This is again this is the homework for the T matrix, right? So T matrix this is another example that you can expect. I'm gonna grade this and then if possible to give you this homework by today at the lab session so that you can have some feedback. But for this, you can solve one problem there in the textbook. Let me see. There are two problems there, 8 and 9. 8 and 9. Try to solve those problems here. I think that's the same problem. Number 9.
Thank you.
On page 89. And then the transformation arithmetics that we discussed last time, to reach to certain locations, find out a known transformation based upon all the known transformation. That's another possible questions in the test number 1. And then tolerance, shaft and the fault tolerance, that might be another possible question. Test number 1 also, in part B. In part A, I'm going to probably use the either textbook and then the handouts to put some questions about the chapter 1, and then 2 and 3. Not 3, I'm sorry, 3, in chapter 3, this is again the end of the part of the test number 1 because we will not have a chance to review everything by Monday. So the chapter 1, 2, part A will be coming from chapter 1 and 2. Okay, the 1 and 2. So focus on the handouts, and then if you can't understand something, then go back to text and rhythm to prepare for part A. But part B, most likely chapter 2 and 3. Chapter 1, I don't see anything analytic solution type problems that I can make on 1, but 2 and 3 definitely up to this one right here. Okay.
Part A is vocab, right?
Huh?
Is part A vocab?
Yeah, part A is a multiple choice.
Okay.
So I'm gonna try to put some about anywhere from 10 to 15 questions. Okay. Any question for test number 1?
How many questions in part B?
Part B, thinking about maybe 3 to 4. Okay, so now what we will do is to move on to the next sections of chapter 3, which will be about the 3D modeling schemes. Okay? So now you'll learn some basics about the modeling of how to operate the object in your space, design space, for transitional transformation or rotational transformation. But there is some schemes that we need to understand, such as so this one. So what we discussed so far in chapter 3 is understanding coding system. And then also we discussed about description of frame, and then the mapping into frames. That's all the things that we discussed so far. And then the understand general transformation. General means that the translation and rotation all involved. And we discussed about transformation arithmetics. And then general form of rotation. We discussed the two general forms. One is a fixed XYZ. The other one is the Euler angle. Moving Euler angle. Those are things that we discussed already. Okay. So now we'll move on to the last part of this chapter, 3D modeling schemes. Okay. So in scheme, there are a couple things that I want to just point out. These are things already you already understand through the first section of the this 3D modeling. But just as a quick review, Cartesian coordinate system is the a space, a design space that we put together parts to actually realize your ideas, okay, if you have something in mind. And then global coordinate system, GCS, is basically a frame that's fixed on the ground. So always the first reference point of the first reference coordinate system fixed on the ground is what we call global coordinate system. And then the work coordinate system or local coordinate system, those are the system that's attached on each model. Okay, so each individual model, if you have 100 parts that all come together, you will have 100 of the workspace. Okay, work coordinate system or local coordinate systems. So that's how we differentiate them. And then instances, this is a term that we utilize for 3D modeling for some primitives displayed on the screen. What I mean by saying primitives is that there are some predefined primitives, like cuboid, cylinder, sphere. These are all some examples, not everything. Some examples, but you can actually have your own primitives that you define, like screws or rivets, whatever. So those are the things that are saved in your database. And then whenever you bring this up on your screen, by applying some rotation and translation and then the magnification, that's instance. Once it is realized on the screen, that's what we call instances. And then in this picture again, we have said this many times, but the main core system is what? Is it global or local? So global, fixed on the ground. And then local right there is what? Work core system, okay? Where you work to develop your own part. So that's pretty much the basics of the 3D model. And then this is the some examples. There are some. These are some examples of the 3 different models that we will discuss today. Those are wireframe. One is a wireframe. The other one is surface model. and then the third one is solid model. So what do you think is the model technique that's used for the red one?
Wireframe.
My friend, everyone would agree? That's correct. How about the Roomba? How many of you think that the Roomba is designed by surface or solid? Surface. Solid. Whoever didn't raise your hand. What is, you're in some in the middle? Try surface. Solid. What? Surface. Solid. Nobody? So you think this is solid? That's
Yes.
correct. How did you know?
Looks solid.
Huh?
Fancy lines on the surface.
Looks like solid. Okay. Anyway, but there are some, can anybody tell what's the difference between these surface and solid?
Between
Well,
the geometry of the
sides
surface.
describing the
Uh-huh.
curves.
The surface is only giving you the texture and contours of the surface of the part. The solid shows you,
Show colors, texture?
well, I don't know about texture, but it shows you, it differentiates the part with, not only by color, but it only shows it as one solid entity. There's no contour lines or wire outlines in it.
Well, okay, that tells a little bit, but not exactly the point.
Okay.
Because the, this is just, I'll just show this to you, because some surface models looks like this. So at the moment, I don't expect that you guys be able to understand and then tell everything about differences between these three modeling schemes. But after we finish these sections, you should be able to tell, okay, by looking at something, hey, this is solid. But again, the images or model, you can sell, you should be able to say this is surface, okay? That's a whole point. But again, there are so many different types of schemes. For example, in Hollywood, the movie industry, they use totally different modeling techniques. They have a realistic hair display models based upon some fluid mechanics and stuff, and then water, how to express with water, okay? Water splashing and everything. Those are also another techniques. It's not part of this. So it has been advanced so much now, but the engineering, for the engineering purpose, these three are more than enough at the moment. Maybe it will be advanced more and more, and I mean, some people are trying to advance it, but these three modeling techniques are very basic, okay, 3D model, to understand everything else. So once you understand these three, I'm sure you will be able to invent your own or understand some other schemes, okay, based upon this, because most of them are based on these three models. When it comes to engineering parts. So let's talk about the wireframe first. Again, this is a wireframe, and anybody can tell what's the problem with this wireframe.
You can see through it.
You can see through, but what? Can you
Can't tell
tell?
what's on the front or the back.
Yeah,
It's a
can
door,
you tell
it's a
this
window.
door is in the back or front?
Kind of a mess of lines in it now.
It's a little bit difficult to identify where each parts are, right? It's kind of a little bit ambiguous until you rotate to understand everything completely. So wireframe has good, we'll call it the basis, and then its own benefits to show you all the skeletons of the structures, because you see everything all together in one shot. But it's difficult for us to understand everything, right, about the structure. And then this is a surface model. Again, this is a little kind of wireframe, not exactly the wireframe. And the surface model is going to be, the reason I'm showing this is because surface model is most likely based upon the wireframe. You have to have your skeleton, just like our body. You have your skeleton, you put your skins, right, to make a body, but same thing happens right here. So you have the wireframe, which is your skeleton, and then you start, you're putting textures and colors with the surface together to make the actual surface model, right? That's the difference between surface and the wireframe. This is what? This is a good example of solid model. Anybody can tell the kind of difference between this and then the skull surface model? What is the kind of a distinctive difference between these two? If you look at this, is there a kind of a very smooth surface on it? Smooth surface? There's smooth surface, but the curved surface, very complicated. If you see the skull right here, you see that a lot of complicated surface right there, very specific surface, okay? Bio-natural surface right there. But here, not too much of natural surface. It looks like it's all artificial. Why does this look like it's all artificial to us? It's not, looks like, you can tell this natural thing, this is a artificial thing, but this one seems to be artificial. Why? Because
Simple geometry.
there are a lot of simple geometry, all put together. Most likely is a part of the box, and then the sphere sometimes, or circle, cylinders, right? And then straight lines, and then plane. It is just a combination of what? Simple geometry. It's not a natural thing. There's nothing like this in that nature, right? So that's one of the quick hint to be able to tell the difference between the surface and then solid. Because most likely, what seems to be more artificial is solid. More what do you call it? The natural, that's surface. Right? So when people are trying to develop or design a next generation vehicle, what do you think? People try to make it more look